Hello friends, welcome back to my channel, and in this video we will solve simple problems in the topic of integration involving unit, step and Dirac delta functions. The problem statement goes like this. We are asked to evaluate these three integrals. So first one is integration of the product cos tau and u of tau, and integral limits are from minus infinity to t. And second integral is the integration of the product cos tau and delta tau. Again, integral limits are from minus infinity to t. And third integral is product of three functions cos tau, u of t minus tau and delta of tau, and we have to integrate from minus infinity to plus infinity. So let us solve these problems one by one. So what is the first problem? Let us call the first integral to be x1 of t, and that integral is given by integral minus infinity to t cos tau u of tau d tau. So you see that there is a product of two signals. One is cos tau and u of tau. Let us see how does the plot looks. So this is our cos tau, which is a cosinusoidal function which exists from minus infinity to infinity, and second function is u of tau, which is unit step function, which is 1 for t greater than or equal to 0 and 0 for t less than 0. So because the unit step function starts at 0, the product of these two functions also should start at 0. For t less than 0, product would be equal to 0, and hence how does the product look? The product will look like this. So cos tau u of tau, the product will look in this fashion. So once we get this product, we have to integrate this function, correct? So that is the question. So we have to integrate this function, and if you see that the integral limits are from where to where? Minus infinity to t. And what is t? It is a variable. So what happens when t is less than 0? I have to integrate from minus infinity to t, and let's assume that t is less than 0. So for that case, we don't have any signal, and hence for that case the integral would be equal to 0. Okay, and what happens when t is greater than 0? When t is greater than or equal to 0, we have the function which is cos tau, and hence the integral limits actually should be from minus infinity to t, but the whole product exists only from whole product starts at 0, and hence overall integral would be from 0 to t. So that is what we have seen here. So when t is greater than or equal to 0, the integral would be like 0 to t cos tau d tau, and this integral is simple. Why? Integral of cos tau is sin tau, and integral limits are from 0 to t. After substitution, we get this result, and hence what is this integral equal to? That integral would be equal to 0 when t is less than 0, and that is sin t when t is greater than or equal to 0. Now let us look at the second problem, which is integral minus infinity to t cos tau delta of tau d tau, and let us call this integral to be x2 of t. So cos tau we have already seen, so that is a sinusoidal function which exists from minus infinity to infinity, and delta of tau is a Dirac delta function which exists only at 0 with a strength of 1. So what is that we have to do? We have to multiply cos tau with delta of tau, and because delta of tau exists only at origin, the product also would be equivalent to delta of tau. Y at t equal to 0 for at tau equal to 0, cos tau is equal to 1, and hence there won't be any change in the strength of the Dirac delta function. So what is the summary? The product of cos tau and delta of tau is same as delta of tau. So from this plot, what is that we observe? We observe that x2 of tau would be equal to 0, because the integral limits are from where to where? Minus infinity to t. By again using the same analogy what we did for the previous problem, what happens when t is less than 0? If integrate from minus infinity to t, and if t is less than 0, we don't have any signal, and hence that integral would be equal to 0. When t is greater than or equal to 0, let's say t is somewhere here, if integrate from minus infinity to t, so that integral limits include Dirac delta function, and that fellow's area would be equal to 1. So for t less than 0, we don't have any signal which is equal to 0. For t greater than or equal to 0, we have a integral of Dirac delta function, and what would be that equal to? So in area of Dirac delta function would be equal to 1, because The integral limits include the Dirac delta function, and hence what is the summary of this integral would be equal to 0 when t is less than 0, that is 1 when t is greater than or equal to 0, and we know that this is nothing but our unit step function. Okay, let's go to the third problem which is given by this. So this integral, let me call it as I3 because you get a definite answer for this. So I mean you get a value, single value for this. You don't get a function which varies with respect to time, and that's the reason why I called it I3, because the integral limits are defined from minus infinity to infinity. So what is this integral? This is nothing but the product of these three signals. One is cos tau, and the second one is u of tau minus 1, and third one is delta of tau. So let us plot cos tau, which is already there. Second one is u of tau minus tau, which is unit step function shifted to the right by 1 unit, and third function is Dirac delta function, delta of tau. So we have to multiply these three functions. So you can clearly see that. Let us cos tau, let us see what happens if you multiply first two guys. So cos tau and u of tau minus 1, the product exists from 1, and for less than 1 the product is 0, and for greater than 1 that is same as cos tau. And after the product, after multiplication of cos tau with u of tau minus 1, we have to again multiply with Dirac delta function, but this Dirac delta function exists at origin, and hence what happens, the overall product does not have any common region, and hence this integral will be simply equal to 0. Okay, I think you have understood the concept of integration involving cosine functions, unit step function, and Dirac delta functions.